I'm Cheol Ho Choi from Kyungpook National University, South Korea. I'm a quantum chemist, mostly trying to develop new quantum mechanical theories. But recently, we got some interested in machine learning, so we are very happy to share some of our recent results. The motivation, well, as you can see here in the middle, very nice looking picture, right? Dr. Kiriya Nakata, who has an older work here, and he's very much interested in machine learning, and also he is a quantum chemist too. Everybody wants to use machine learning, so we were also curious about the power of machine learning. So we tried to use it, but in this particular case, we tried to think about whether machine learning can really use for chemical reactions like ALD, atomic layer deposition reactions. In the figure, as you can see, here, silicon 111 surface, hydroxyl terminated. Basically, ALD is composed of consecutive chemical reactions to create really fine surface layers. But in this reaction, we use really the popular, the most well-known molecular precursors. Your left-hand side here is trimethyl aluminum, and on the other side, you have water. And we really want to know whether machine learning can help us understanding the chemical reactions on this silicon surface. Basically, what ALD is the chemical reactions. What is chemical reaction? Which is bond making and breaking, which is very challenging because chemical bond making and breaking are the quantum mechanical phenomena. Therefore, no other method can be used to describe this except quantum mechanics. For example, here, if you send TMA to the surface, here I have an arrow here, right? So it creates interfacial chemical bond between aluminum and oxygen. And right after that, some of the hydrogen on the surface is trying to make a reaction with the methyl group, creating, you see that the methane gas. This is interesting. And while doing that, it creates another chemical bond here, and so on. It's quite complex. Also, this bond making and breakings need a very high level of quantum mechanics. It cannot be done by classical ending. So we need quantum mechanics to describe this. But we all know, maybe some of you know, they are very expensive, so we want to minimize it. Well, but in order to have a good machine learning training, we need a lot of data, but we cannot produce them many because quantum mechanics is expensive. So we have some kind of dilemma here. So I listed some of the quantum mechanical programs like games. That's one of my co-developer of games, and the BASF, and there's Siesta. So we try this, and the particular combination of programs we use here is the Siesta, which is for quantum mechanical calculation. And also we use a DeepMD kit, which generates MD parameters through machine learning. And finally, we use LAMPS to perform molecular dynamic simulations. Well, these three programs can do each of their own works, but what we really need here is optimum data set for machine learning training. Otherwise, we're going to spend a lot of our time and efforts to generate data for machine learning, right? So we really need, you can see that we need one more ingredient. By the way, I put it here, NVIDIA GPU. I think this is the thing I need to do with for this summit. Essentially is the smart sampling. And this has been done in over quite a long time in the molecular dynamics community. For example, in this case, look, this is your reactants, for example, okay? And this is your product here. Now, what we need to describe is chemical reactions in between the two. So basically, we need those structural informations in between the two connecting these reactant products. It doesn't have to be right on this dotted line, but it's better to be around this. So we need to sample the structural data in these blue regions. That's what we need. We don't need any other data far from this rectangle products here, right? So how can we achieve that? Well, we thought about this a couple of years ago, by the way. 2018, we developed a kind of interesting technique. We call it ODP as one-dimensional projection technique, which is essentially what it's essentially doing is that it's mapping 3n-dimensional problem into just two. What is n? N is number of atoms here. Okay, so if you have 1,000 atom here, then your dimensionality is 3,000 versus just two. Okay, this is our technique. So you just need to control just the two variables to be able to search for this particular case. So basically what it does is that suppose you have a reactants again here and products here, X is any structure in between the two. Okay, then so you can project this point into this particular vector that is connecting P and R. So now X can be decomposed into two components, two rads here, solid rads and dotted rads, okay? So the solid rad is telling us that how much direction has been done. For example, if you are here, then if you consider this is 100%, maybe 30% direction is done. And the dotted line is representing the deviation from this particular straight line. So if you are really far away from this reaction path, then this dotted line will be very, very large. So by using these two vectors, what you can do is you can do two-dimensional umbrella sampling. That is exactly what we did. And so this is a bit complicated, but this is the overall structure of what we actually did. And initially, you need some small set of quantum data. Otherwise, you have nothing, right? So using those data, you can train machine learning to get the and this is a deep MD gives you MD parameters, initial parameters, which is not good, but it's still you have something. Using this, you perform machine learning molecular dynamic simulations on the condition of ODP-assisted umbrella sampling. This particular combination generates the particular structures that are near to the reaction pathways. Okay, this is somehow guaranteed. So once we have those structures, you just do full quantum calculus, which is easy, although it takes a long time, and generate energy and gradients, and you do the machine learning, and you update molecular dynamic parameters because you have more structures. Now, once you have more refined MD parameters, you perform again the same thing and generates more structures. And then you continue on this iterative process on and on. Not indefinitely, by the way, we have to stop somewhere, right? So we have to figure out where to stop. So we propose dual validation here. So your ODP-assisted umbrella sampling will generate free energy surface because you perform molecular dynamic simulations. Using these, we can calculate free energy difference between iterations, right? This is exactly what it is. So you can see that it converges. The difference becomes smaller and smaller. And eventually it will arrive 0.2 kilocalories per mole, which is very small in terms of chemical quality. So I would say this would guarantee some chemical quality. So at about 7 or 8 iterations, we probably have pretty good molecular dynamic parameters through machine learning. And there's yet another, of course, you do the machine learning training for each iterations, which is essentially just comparing the exact value and the predicted values, right? And that will give you data accuracy. So I would call it, the first one is chemical quality, and then second one is data accuracy validation. So we kind of have a dual validation. So according to our simulations, this is about 7 or 8 iterations is good enough. Once you have done this, now you are ready and go ahead for the production runs. Because now you have MD parameters, this is fun time. You just generate lots of data because all you have to do is just a machine learning MD, right? But using the particular coordinates. X-axis represents the chemical reaction coordinates and Y-axis represents the deviation from the reaction, the straight line of the reactions, right? So Using these, we can map out all possible, any kind of structures you can obtain in this. This is in fact the free energy surface, which is not potential energy surface you get from the quantum calculation. This free energy surface includes entropy effect too. So this is really the complete information. Here you can see that the interesting points right here. By doing this, by the way, this kind of free energy surface cannot be generated by quantum calculation because it requires so many data. But with this fitted machine learning fitted parameters, there's no problem, right? So maybe I should first point out that this might be the first free energy surface calculation without using quantum calculation. So ML, machine learning MD, can really possible, and it can really describe bond making and breaking. And we found various previous unknown structures like this. So let me just point out this particular ones. This you see that plus and minus, which is in the chemical term, this we call the Zwitter ionic structure, which was never been reported before. So by analyzing these, we can see the kind of possible structures and the kind of the right reaction path. For example, these red things are the high energy area, so the reaction will not go through this red, but mostly goes through the flat area. So in the case of water chemical reactions here, you see that very characteristic channels of the preferred pathway here, right? So this cannot be obtained by any means, but with this, we were able to see this, and we can check the corresponding geometries, and then we can understand the reactions. This is a one-dimensional plot of the previous PMF. We actually study 6 different chemical reaction pathways. So 3 of them here and 3 of them there. The first one corresponds to trimethyl TMA chemical reactions. You can see that what the main difference between the two is that here, from the initial point, you do see some barrier, reaction barrier, right here. But in the case of water, it's just going down, right? Not much of barrier, meaning that the water can easily undergo surface chemical reactions while TMA has some problems, some issues. So initially, it would just stick there. It would not make any further chemical reactions on the surface. So extra time or extra energy might be necessary to overcome these barriers. Using parameters, you can do many other interesting things. Like in this particular case, we try to do some kinetic simulations here. You send the TMA to the surface, right? Some of them can just bouncing back, but some of them can make useful surface chemical structures like this. And what we did was that we simply change dropping rate or velocity of this molecule to the surface, see whether change of velocity does anything to the ratio of these two possible events. So this is an interesting plot we think that we have here. We did not expect that this x-axis represents the velocity. Okay, then the y-axis represents frequency. So we observe the maximum absorption rate at a particular speed. So this is interesting because at a particular speed, you have a maximum chemical reactions that we can form here, which is thing that this has to do. There are some competing factors here. If you have a very slow speed, then the residence time, staying on the surface, it increases, but you don't have enough kinetic energy to make a chemical bond. But on the other hand, if you send it too fast and the energy is too much, so that it can quickly bouncing back. So you have a less chance of making chemical reactions. So this is also interesting thing that you could study. So we introduced here our ODP idea, which kind of allow us to generate the most relevant data for this particular chemical reactions, which somehow minimize the necessary quantum mechanical calculations. So I think that this is quite useful. So I hope that this is a very simple idea. So you could use for your research too. And the second one we found is that ML can be good for chemical reactions. So it can really do bond breaking and making. which is amazing because only quantum mechanical method can do that. But now machine learning MD can also perform such bond making and breaking, which is to me quite amazing and quite useful. So we can use for some other cases too. And we found, by doing this, we found that some unknown surface structures, and there is new reaction path. I have not talked about the details of the reaction pathways, but we located multiply different reaction pathways, which wasn't known before. Also, we played some dynamics with the machine learning MD can give us probably a way to control ALD processes. I'd like to thank my group here. You can see that quite international. And I really like to thank NVIDIA for your help. And thanks very much for your attention.